Okay, so I'm going to get started. So first of all, thank you for the invitation to make this presentation. Second of all, I was invited to talk about the Majorana versus Dirac question that permeates neutrino physics in lots of different ways. And this is meant to be a semi-pedagogical presentation. So my job will be to tell you about what the question is, why we don't know the answer to the question, and I'll talk about the different ways in which we hope to be able to distinguish neutrinos that are Majorana from neutrinos that are Dirac. And I will spend a little bit of time talking about the traditional way of doing this, which is to look for neutrinoless double beta decay, which, by the way, is the subject of this picture that I have here, my first slide. And but I'll also try to go over a lot of less orthodox ways of distinguishing Majorana neutrinos from Dirac neutrinos, which I hope will give you a sense of what the question is about. Okay, so the key question about whether the neutrinos are Majorana or Dirac falls back to, if you have a massive fermion, how many degrees of freedom do you need in order to describe this massive fermion? And the way I'm going to get started is to remind you about how we talk about electrons and how we think about electrons. And the idea is more or less straightforward, and we often don't think about it, but it's worthwhile going over this a little bit slowly. So if you have a spin-a-half particle, it has more degrees of freedom than a scalar particle. And one way in which we can label degrees of freedom is by labeling them according to their helicity, for example. So that means, if I have an electron, I can speak about an electron that has left-handed helicity. Now, if I have a theory that has a particle in it that's a left-handed helicity electron, that particle will have a CP partner. So I can apply the CP operation on this particle, and this operation tells me that there's another particle that must exist, which is a right-handed positron. That's the CP partner of the left-handed electron. Now, there's another thing that's special if the particle has mass, which is if we live in a world where we measure a massive electron that in the laboratory has left-handed helicity, I can also conclude, without doing any new experiments, that there has to be another state in the system, which is a right-handed electron. And those two states have to exist because they're related to one another by a change of reference frame. And if you know that the electron mass is not zero, if you ever observe a left-handed helicity electron, a right-handed helicity electron has to exist as well. A different way of thinking about this is, instead of talking about electrons with helicity, we can go to the rest frame of the electron because it has mass. And the statement I'm making is that if you ever do an experiment and you determine that the electron has spin up, that you don't need to do a different kind of experiment to establish that electrons with spin down also exist, because you can just change reference frames by turning upside down, and what used to be a spin up electron becomes a spin down electron. So that means that at the end of the day, this particle that we call the electron requires 4 degrees of freedom to be fully realized because of Lorentz invariance and because of other properties of spacetime. So that means that there's a left-handed electron, a right-handed positron, a right-handed electron, and a left-handed positron. By the way, all of these particles are related to one another by different operations, including parity. Parity relates the left-handed electron to the right-handed electron, and charge conjugation relates the left-handed electron to the left-handed positron, and the right-handed electron to the right-handed positron. So what about neutrinos? So if you have a massive neutral fermion, it turns out that the story is a little bit more exciting than the electron case because you have choices. One choice is very similar to the electron story, which is if you know that a left-handed neutrino exists, it has a CP partner, which is some right-handed state, which for the sake of argument, we're going to call the right-handed antineutrino. So CP tells us that the new L state is associated to a new R bar state. On the other hand, just like with the electron, if the neutrino has a mass, for every left-handed helicity neutrino, there must be a right-handed helicity neutrino. So there's another state that I can define, which is the right-handed helicity neutrino. So again, I can follow the story all the way through, and I can end up in a situation where I have a left-handed neutrino, a right-handed antineutrino, a right-handed neutrino, and a left-handed antineutrino. Now, this is where the choices come in because I have the freedom to choose what I'm calling the right-handed neutrino and the right-handed antineutrino to be the same particle. That's a choice that I can make, and it's a choice I don't have with the electron because you notice that this state, which is the CP conjugate of the left-handed electron, has positive charge, while the Lorentz partner of the left-handed electron, which I'm calling the right-handed electron, has negative charge, and those two states are obviously different states. But in the case of neutrinos, I can equate the right-handed neutrino with the right-handed antineutrino, and I can postulate that that's the same particle. So that means that even if I have a massive neutrino, it is possible that that requires 4 degrees of freedom to describe, but it's also possible that it requires 2 degrees of freedom to describe. So if the neutrino requires 4 degrees of freedom, we call that a Dirac neutrino. If it requires 2 degrees of freedom, we call that a Majorana neutrino. Now, 4 and 2 are very different numbers, so it's fair to ask how come we don't know what the answer to that question is. And the reason for that is if the neutrino mass were 0, I wouldn't have been able to ask the question. There's no such thing as a Dirac massless fermion and a Majorana massless fermion. They're just a massless fermion. There's no such thing. There's no distinction between one and the other. And what happens with the story that I was telling you before is that if the neutrino mass is 0, then this Lorentz arrow here doesn't exist. And it means that the only states that you need are the 2 states here at the top. And even if those 2 states here at the bottom exist, they're not really related to neutrinos anymore. There's some other state, which I can call something completely different. So that means that the question that we're trying to ask only makes sense if the neutrino mass is not 0. And what that means is if you can devise an observable that can distinguish if the neutrinos are Majorana or Dirac, that observable or the amplitude or the probability for that observable to be realized has to vanish when the neutrino mass goes to 0. And the way to think about this is if when I set the neutrino mass to 0, I can't distinguish Majoranas from Diracs, it stands to reason that in the limit where the neutrino mass goes to 0, any observable that can answer the question should also become trivial because you can't answer a question that you can't ask. Okay, and the challenge for us is, of course, neutrino masses are really small. So that means that the probability for anything to happen will be proportional to the neutrino mass divided by some typical energy scale of your problem. And it turns out that for any experiment that we can think about, the typical energy scales of the problem happen to be much, much, much bigger than the neutrino mass. Now, there's an extra wrinkle to this story, which is not unrelated, but peripherally related, which is the neutrinos only interact via the weak interactions. And it turns out that the weak interactions are chiral, and they're actually purely left chiral. Let me tell you or remind you of what that means by looking at something like muon decay. And let's say I have muon decay at rest, and let me ask about the properties of the electron that comes out. And it turns out, because the weak interactions are purely chiral, and because the electron mass is small, the electron that comes out will be mostly left helicity, mostly left-handed. And it will have a small probability of also being right helicity, and the probability is proportional to m over m electron divided by the muon mass, if I'm calculating this in the muon rest frame. I can calculate the CP conjugate of this process, and the CP conjugate of the process is the mu plus decay, and it turns out that the positron that comes out, just like the electron is mostly left-handed, the positron that comes out is mostly right-handed. Okay, so that's how muon decay works. We can now talk about neutrino production, let's say in pion decay. The story is the same. It's a weak interaction process. That means when a pi plus decay, a neutrino comes out, and that neutrino will be mostly left-handed helicity. And if I'm calculating this in the pi unrest frame, there's a tiny probability that you get a neutrino with a different helicity. I can now talk about the CP conjugate of that process, and the CP conjugate of that process will produce the CP conjugate of the neutrino. And let's not call it the antineutrino, it's just the CP conjugate of the neutrino. That state, by the same story, is mostly right-handed. And the reason this is important is, again, when the neutrinos are going to be detected later on, they will also be detected by the weak interactions. And it turns out that, when the left-handed helicity neutrino hits something, the current that it will speak to will be the current that connects it to the electron. When the CP conjugate of the left-handed neutrino, which is purely right-handed, hits something, it will be connected to the version of the weak current that knows how to produce positrons. So what this means is, whenever you have neutrino production and detection, every time you produce what we normally call the neutrino, that will be a left-handed state. Every time that state hits something, the weak interactions associated to it will produce electrons. And if you talk about the CP conjugate of that process, it will produce a right-handed state, which we often call the antineutrino. That state will interact via the weak interactions and only knows how to produce positrons. So that means if we ignore the neutrino masses, everything behaves as if the neutrino and the antineutrino are different particles, or they're different states, and they're always related by this CP conjugation. Now let's talk about what happens if the neutrino mass is not zero. It's the same story. Imagine I have a process where an electron hits something and produces a neutrino. Because my initial state was an electron, the object that I produce will be mostly left-handed with some small probability of being right-handed. Now let's assume that this object here is going to hit something. And when it hits something, just like I was telling you before, most of the time it will behave like the left-handed helicity object. And the left-handed helicity object, when it hits something, it's really good at producing electrons, and it doesn't know how to produce positrons. Now, if by chance the neutrino chooses to behave like the right-handed helicity object, the right-handed helicity object is where the Majorana versus Dirac question comes into play. If the neutrino is a Dirac fermion, this right-handed helicity object here is what we would call a right-handed neutrino. And it turns out that a right-handed neutrino doesn't participate in the weak interactions. So that means it doesn't do anything. It means that your total rate would be a little bit smaller than you would have naively anticipated. Now, if the neutrino is a Majorana fermion, the right-handed object that I produce here does all of the same things that the thing that we normally call the right-handed neutrino does. And in particular, it can speak to the weak current in a way that produces positrons, just like I was showing you before in this line over here. So that means that it is possible, if the neutrino is a Majorana fermion, that it will choose to behave like this right-handed helicity object, and the right-handed helicity object is allowed to participate in the weak interactions if the neutrino is a Majorana fermion, which means that I can produce a positron having started out with an electron in the initial state. And this, of course, violates lepton number, and I'll mention that in the next slide. But the message I want to leave you with is the probability for that happening is proportional to the neutrino mass squared divided by the typical energies of your system, which for any experiment that you can think about will be super tiny. So this is a probability that will be 10 to the minus 18, 10 to the minus 20. It's almost impossible to think about observables that will be sensitive to this. And I'll come back to this in the remainder of the talk. Now, the way that we often talk about this is in the language of lepton number. If the neutrinos are massless, I can assign lepton number to the electron, the muon, and the tau, and the neutrino. They have lepton number 1. And the antiparticles, the positron, the mu plus, and the tau plus, and the CP conjugate of the neutrino, they would have a lepton number -1. And as far as we can tell, in nature, all physics processes preserve this lepton number. However, if the neutrino is its own antiparticle, you notice that the neutrino and the CP conjugate of the neutrino are the same state up to a change of helicity, right? A left-handed one turns into a left-handed, right-handed one, but they're still the same state. So you can't assign equal and opposite quantum numbers to the same object or to two objects that are related by parity. So what that means is if the neutrinos are Majorana fermions, I can't define lepton number. So lepton number can't be an exact symmetry of nature because it's just not a property that the neutrinos can have. That means that usually when we talk about looking for whether the neutrinos are Majorana fermions, what we do is we look for lepton number violation. Because if lepton number is conserved, the neutrinos have lepton number, they must be Dirac fermions. But if lepton number is violated, they are allowed to be Majorana fermions. As something that everybody has heard about in the past, I presume, is the best way to look for the violation of lepton numbers to look for neutrinoless double beta decay. This is a process where you start out with a nucleus, you end up with a different nucleus, and you emit two electrons, and no neutrinos get emitted. And you notice that your initial lepton number was 0, your final lepton number is 2. This violates lepton number by 2 units. You can try to calculate this. The baby version of this calculation is two W bosons annihilating into two electrons. The W bosons live inside of the neutron. And you can do this calculation, and it turns out that the probability for this to happen, as advertised, is going to be proportional to the neutrino mass, and it's proportional to some effective neutrino mass. That is a linear combination of the neutrino masses that we have constrained using oscillation experiments. And when people make plots and they talk about the sensitivity of their neutrinoless double beta decay experiments, they usually talk about setting a bound or being sensitive to what's called this effective neutrino mass, called MEE. And right now, we can calculate what MEE should be as a function of what's the lightest neutrino mass, because that's something we don't know. We only know the mass square differences. And it turns out that if the neutrino mass ordering is inverted, this observable has to lie in this green band. If the neutrino mass ordering is normal, this observable has to lie in this red band if the neutrinos are Majorana fermions. And what experiments are doing is they are in the process of probing this green band, and they're thinking about how can we build experiments that start to go beyond and give us sensitivity beyond where this green band lies. So there's a lot of experimental activity, which I'm not going to talk about in any detail. There's several experiments currently taking data, and there's a whole bunch of Aton scale projects that are being thought of and designed and funded and so on. Just to give you a sense of how this works, this is a very, very busy plot. I'm not going to look at all of this. You're looking for the neutrinoless double beta decay of xenon. This is from the Camlin-Zen collaboration. And what you measure very, very well is you have this xenon 136 undergoes a process that's the same as this one, except that you emit two electrons and two antineutrinos at the same time. So that's called the two neutrino double beta decay. That doesn't violate lepton number. It's a very rare process that's been observed. In the case of xenon, you get this very, very nice spectrum of the energy that the two electrons carry. And the neutrinoless double beta decay contribution, if it were there, would look like a line, which in the case of this experiment, because of energy resolution, gets mirrored out into a little bump. And what you're looking for then is a bump that lives at the end of the two neutrino double beta decay spectrum. And we have a big, lots of experiments taking data and being planned to start to try to look for this in lots of different ways. So here's a summary of current results in this plot that I showed you before. The colors are different. So you notice that the current generation of experiments is starting to be sensitive to Majorana neutrinos if the neutrino mass ordering is inverted. And their goal, or the goal of the next generation of experiments that will hopefully be taking data in the next decade, is to cover this inverted ordering region. And hopefully we'll start thinking about how to make progress if the neutrino mass ordering happens to be normal. All right. So what I want to talk about for the next 20 minutes or so is what else is there? So we want to distinguish neutrinos if they're Majorana or Dirac. We know that the best way to do it is to do neutrinoless double beta decay searches, but it's worthwhile thinking about other things we could be doing, and that's very hard on the one hand, but it's useful pedagogically just to give us some sense of what Majorana fermions do that Dirac fermions don't do, and vice versa. So I'm going to talk about two different kinds of things. One is, of course, what's going on with neutrinoless double beta decay is we're looking for lepton number violation. So you can ask, are there other ways to look for lepton number violation, and should we care about those? And finally, I want to move a little bit away from direct violation of lepton number, and I want to try to tell you that Majorana and Dirac fermions are different in processes that don't directly violate lepton number. So that's the plan. So are there other ways to look for lepton number violation? The answer is yes. Now, why don't we care too much about that? The reason is sort of twofold. One is the reason we like to talk about neutrinoless double beta decay is because the bounds we get from neutrinoless double beta decay are really, really, really strong. So that means that any other observable that you can come up with will not be as sensitive as neutrinoless double beta decay. So the question is, should we care about an observable that's not as sensitive by many orders of magnitude? The answer turns out to be yes, because when it comes to neutrinoless double beta decay, neutrinoless double beta decay really cares about the electron flavor. So if you have other processes that speak to other observables that have to do with other flavors, they might not be ruled out by searches for neutrinoless double beta decay. One way of thinking about this is you notice that in the case of the normal ordering, this effective mass for neutrinoless double beta decay can be very, very tiny and even zero. That's a consequence of the fact that we're only speaking to the electron flavor, and it could be that things cancel out in the electron sector. So that means if you do experiments that involve muons or taus, there's no reason to expect this thing here to vanish. And actually, it can't vanish for reasons that are not important. So another thing to always keep in mind is that neutrino masses are very small. So that means if you can come up with a typical lepton number violating observable in some other process that's not neutrinoless double beta decay, the typical expectations will be such that you shouldn't be able to see anything. So again, going back to this picture, which I've shown you before, you notice that neutrinoless double beta decay experiments are starting to be sensitive to expectations from neutrino exchange, which is this picture over here. If we made this plot for another observable that's not neutrinoless double beta decay, the sensitivity of those observables to the equivalent combination of neutrino masses will be much, 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 much worse than where expectations lie. So the question then is, should we still care about this? And the answer is yes, because again, searches for lepton number violation are looking for lepton number violation. And the way in which lepton number violating physics connects to neutrino masses is not one-to-one. Even if the neutrinos are Majorana fermions, it is possible that the physics responsible for lepton number violation only speaks to the neutrinos very feebly in such a way that maybe the rate for a lepton number violating process is much, much bigger than naive expectations. And just to give you a flavor, these are all different kinds of processes that violate lepton number that we have bounds on. This is from the particle data book. Neutrinoless double beta decay is here somewhere, over here where the arrow is. And actually the story is, the page is a little bit longer. So if you look in the particle data group, that's what the whole list is. And I don't want to speak to most of these processes. I just want to do some advertisement, which is if you don't like neutrinoless double beta decay, but you want to do the second best thing, the second best thing are searches for mu minus to E plus conversion in nuclei. And one reason to get excited about this is that we do have new experiments that are being built to look for mu minus to E minus conversion in nuclei, which is a violation of a lepton flavor, and that some of those experiments can also look for mu minus to E plus conversion. So we expect these bounds to improve by at least a few orders of magnitude, if not many orders of magnitude, in the next 5 to 10 years. Okay, so what I want to do now is to talk about, is there a completely different thing you can do to distinguish Majorana neutrinos from Dirac neutrinos that does not involve directly the violation of lepton number? And the answer is yes. Now, I do have to say that I haven't thought about this very, very carefully, and whether we can always spoil some of the observables that I'll be talking about by introducing new physics. And hopefully you get a flavor of that once I start giving you some examples. But I'm going to go and start talking about how are Dirac fermions and Majorana fermions different and how that would show up. So let's go back to reminding ourselves as to why we don't know if the neutrinos are Majorana or Dirac. The reason we don't know is that neutrino masses are very small. Of course, when you say that something is very small, you really mean that the neutrino masses are very small relative to the typical energy scales in your experiment. And what happens with neutrinos is that in any experiment that we can think about, the neutrinos are always ultra-relativistic. Okay, so that is the challenge. And what this implies for us is that if we want to look for answering if the neutrinos are Majorana or Dirac, we kind of have two big choices. One is the one that I've been talking about, which is we want to find something that only Majorana fermions can do relative to Dirac fermions. And one example of that is to violate lepton number. And of course, the other thing we can do is we can do an experiment where the neutrinos are not ultra-relativistic. So that's what we're going to talk about. Now, I want to remind you of the fact that even if your neutrinos are not relativistic, they're still at the mercy of the weak interactions. And of course, weak interaction cross-sections at low energies, they grow with the energy to some power. That means that as you start working with lower and lower energy neutrinos, the cross-sections are going to become super tiny. Okay, so that is the big challenge of working with not ultra-relativistic neutrinos. What I do want to show you some examples of is the fact that on the positive side, if you could do these experiments, the distinction between Majorana and Dirac will be very, very apparent. It will not be a problem at all. It will be a big effect. So we can start asking ourselves, how do we find neutrinos that are not super relativistic? And there are a couple of different things we can explore. One, which I'll talk about briefly, is the cosmic neutrino background. That is known to be a source of neutrinos that exists, and they're definitely not relativistic, not ultra-relativistic. Another thing is, if we can't work with neutrinos that have ultra-low energies for lots of reasons, maybe we can consider a nuclear reaction or a physics process where the neutrinos are produced with very, very tiny energies, and maybe that's something we can try to exploit. And finally, I'll say some words about neutrinos that decay. And again, if you see a particle decay, you are secretly violating the approximation that that particle is ultra-relativistic. So let's talk about the cosmic neutrino background. It is a thing that we know exists. We're pretty sure it's made out of neutrinos, and it's super cold today. So that means if you were to detect one of these neutrinos from the cosmic neutrino background, the typical kinetic energies are of order 10 to the minus 4 electron volts. That's a lot smaller than at least 2 of the neutrino masses. So we're definitely working with non-relativistic neutrinos. The other good thing is that there are lots of them. People have been talking about ways of detecting these neutrinos by, let's say, stimulated beta decay. So this is a process where a neutrino comes in, hits a nucleus, and produces an electron. So beta decay would be the neutrino goes to the other side of this equation. So the way we want to look at this kind of process is our kinetic energies are very small. So if we pick a nucleus that already knows how to undergo beta decay without any stimulation, you notice that the threshold energy for this process here is 0. So that's why people have been excited about this. Now let's ask the question about what happens if the neutrinos are Majorana versus Dirac. And this is a big slide, so let me talk about just bits and pieces of it. And the idea is the cosmic neutrino background is made out of two components. One component that has left-handed helicity and another component that has right-handed helicity. Okay? So we're going to try to measure these neutrinos via this reaction here. Okay, so these neutrinos are not very relativistic. So let's pretend that those neutrinos are actually sitting at rest. And let's look, well, they're moving very slowly. Let's look at the left-handed helicity component of that. The left-handed helicity component of that, when it hits a nucleus, it knows how to produce an electron. If it's not moving very fast, the left-handed helicity neutrino will 50% of the time participate in a left chiral interaction, and it will produce the electron. And the other half of the time, it would like to participate in a right chiral reaction that doesn't exist, so it doesn't do anything. So we get a hit. So the neutrino comes in, and we can produce an electron. Now we can look at the right-handed helicity part of my cosmic neutrino background. The right-handed helicity part is different depending if the neutrinos are Majorana or Dirac. If the neutrinos are Dirac, this right-handed helicity part is the antineutrino, and antineutrinos don't know how to produce electrons. So end of story, the half of the cosmic neutrino background does not participate in this reaction here if the neutrinos are Dirac. If the neutrinos are Majorana, the right-handed helicity component of the cosmic neutrino background are also neutrinos. And because they're not moving very fast, these right-handed helicity objects are happy to contribute half of the time to the left-handed chiral weak interaction that knows how to produce electrons. So at the end of the story is, if the neutrinos are Dirac, the neutrinos can contribute to this stimulated beta decay, and the antineutrinos cannot. If the neutrinos are Majorana, the neutrinos contribute to this stimulated beta decay, just like the Dirac neutrinos did, but the antineutrinos, which are also neutrinos in the case of Majorana neutrinos, also contribute to this stimulated beta decay at the same rate. So the end of the story is, if the neutrinos are Dirac, you get a certain rate. If the neutrinos are Majorana, you get twice the rate, which is very exciting, and it's a big effect. Now, why don't we spend a lot of time thinking and talking about this? I think we want to remind ourselves of the fact that we've never detected this thing called the cosmic neutrino background ever. We are pretty sure it's there indirectly, but we've never seen it. And there's some ideas of how to do it, but clearly, even though we have a huge observable, it's a factor of 2 in terms of rate, the rates themselves are so tiny that we've never seen this before. There's another thing you can be worried about, which is when I measure something, I never measure the flux or the cross-section. I measure the product of the two. And because I don't know if I know the flux of the cosmic neutrino background perfectly, the question becomes, can I assign this factor of 2 to an error bar, or do I know for sure how many hits I expect if the neutrinos are Majorana versus Dirac? And I think people are less worried about this problem, and they seem to be pretty confident that we can calculate the expected number of neutrino hits if the neutrinos are Dirac versus the expected number of neutrino hits if the neutrinos are Majorana. And we're pretty confident that we can distinguish those two numbers even after we include all of the uncertainty that's present. Okay, and I'm not going to dwell on this too much. So I want to give you 2 more quick examples and then I'll stop. One thing which I mentioned is if we can't work with very low energy neutrinos in the initial state, why don't we work with very low energy neutrinos in the final state? So one process we can think about is electron-photon scattering going into electron nu bar. This is an experiment I can think about. I can have an electron at rest. I can shine a light on it, and I can see the electron recoil and produce 2 invisible neutrinos, and then I can, in principle, measure this. We can do the calculation, and if we do the calculation, this is what the cross-section is as a function of the photon energy for very, very low energy photons. And if you look at the plot on the left-hand side, you see lots of really exciting things about this process. One is as you change the photon energy, you start producing the different neutrino mass eigenstates. So your cross-section has these jumps in it, which is really interesting. And you could learn a lot about neutrino masses that way. And the other thing that this figure also shows are the solid lines versus dotted lines. And that's the difference between the Majorana and Dirac. So that's what's plotted on the right-hand side. In the right-hand side, we take the ratio of the cross-section between the Dirac hypothesis and the Majorana hypothesis. And you see that for low enough photon energies, the difference is big. The difference in these cross-sections can be about a factor 4 or 5 or something like that. And the other thing that's exciting and easy and fun to understand is as the photon energy gets bigger and bigger, you lose the ability to distinguish Majorana from Dirac neutrinos, just as I advertised for high energy processes. And high energy here means 1 electron volt. You can't tell Majorana from Dirac. If you're curious, there's a gray region over here, and that's actually what happens if you vary things Majorana phases and so on. So it's a very exciting prospect. And why aren't we excited about this? Because the cross sections are really, really tiny. And you're going to have access to these slides. You can read what all the numbers are. Not only is the number of events laughable, but if you were to worry about backgrounds, the backgrounds would completely overwhelm the physics. So the last thing I want to mention very briefly is what happens when neutrinos decay. And again, this is in the context of the neutrinos being not relativistic particles. And if you can see a particle decay, you could study the physics in the rest frame of the particle. And in the rest frame of the particle, they definitely decay. They are definitely not ultra-relativistic. So we're talking about decays like a neutrino number 3 can go into a neutrino number 1 and a photon, or a neutrino number 3 can decay into the 3 lighter neutrinos, assuming if the mass order, the hierarchy is normal. And you can calculate the rates for these processes, and the rates are super tiny. And that's expected. We know neutrino masses are small, so we can never evade the fact that neutrino masses are small. But nonetheless, we can talk about distinguishing Majorana from Dirac. And what we want to do is to look at a physics process where a heavy neutrino decays into a lighter one and something else, let's say a pi zero or a photon. And it's easy to calculate what's the decay distribution of, let's say, this X particle in the rest frame of the neutrino that's decaying. And it goes like a 1 plus cosine theta multiplied by some number alpha, assuming that the neutrino is polarized. We can calculate the anti-process of this, which is an antineutrino decaying into another antineutrino and another X particle. And the X particle, by the way, is a CP self-conjugate particle. In that case, we can relate those two rates for the neutrino decay to the antineutrino decay, and they look almost exactly the same, except that instead of a plus sign, there's a minus sign. Whoops. As long as CP is a good symmetry. So as long as CP is a good symmetry, you can calculate all of this without knowing anything about theory. This is just conservation of angular momentum. The theory tells you what this alpha number has to be, but it depends on the nature of the theory and how much it violates parity. So that means if we have a neutrino that's decaying, the neutrino will have a particular angular distribution. The antineutrino will have a different angular distribution. Now, if the neutrino is a Majorana fermion, the neutrino and the antineutrino are the same particle. And the statement I just made can only be correct if this alpha coefficient is exactly 0 for Majorana fermions. And that turns out to be the case. So what this means is, if I can observe neutrino decay of this type, if the neutrino is a Majorana fermion, the decay must be isotropic. It's not optional. It has to be an isotropic decay. If the neutrino is a Dirac fermion, the decay doesn't have to be isotropic. That means that if you made this measurement and you saw a decay that's not isotropic, the neutrinos have to be Dirac fermions. Okay, so that's the story. Now you can ask questions about, is this alpha coefficient different from 0? And the answer is, for the theories that we know about, it's definitely not equal to 0. Okay, and I'm going to skip the rest of the stuff that I was going to talk about, but there's a lot of interesting applications of this, not for ordinary neutrino decays, but in the context of there being a heavy neutral lepton that does decay, and everything that I mentioned also applies for heavy neutral leptons. And again, if we ever saw a heavy neutrino, we would also want to find out if that's Majorana or Dirac. So again, just to finalize this part of the story, this alpha parameter, assuming the weak interactions, looks like numbers that are not equal to zero. And if the neutrino has a magnetic moment and an electric dipole moment and a magnetic dipole moment, the radiative decay is also not the alpha parameter is not equal to zero. Okay, I'm going to skip what I was going to talk about last, and then I'm going to jump to my conclusions or the quick summary. So the summary is Majorana and Dirac fermions are very, very different. However, if the mass is zero, they are not different. They are exactly the same. And you can't even ask if they're Majorana or Dirac. It's not a physics question that's allowed. And because neutrino masses are very, very tiny, answering this Dirac versus Majorana problem is very, very difficult to do in practice. So one solution to get around this is to find out what are things that only Majorana fermions can do. And the best thing we have in the market is to look for lepton number violation. Now, this is a very rare phenomenon. And if we ever saw a lepton number violation in nature, it would be a big smoking gun that the neutrinos have to be Majorana fermions. There's another way, which is to try to work with neutrinos that are not ultra-relativistic. And if the neutrinos are not ultra-relativistic, then distinguishing Majorana from Dirac is a trivial thing. However, on the downside, the rates for all of these processes that we can think about, again, because neutrino masses are very small, are going to be super duper tiny. And it's very hard to imagine that we can get to a point where we can see these things. All right, so I'm going to stop here. Thank you for listening.